For our next case study of how to use greedy algorithms, we're going to turn to the application domain of scheduling. That is, how do you schedule jobs on shared resources in order to accomplish some objective. So the domain of scheduling, there's lots of different applications of greedy algorithms. We'll see two in this course. We'll start for today just with the following simple scenario. So we'll assume for today that there's just one shared resource. This resource could represent any number of things. For concreteness, you can think of it as a computer processor. And then there's a lot of different things that got to get done. So for example, there's a lot of processes that have to be handled by this processor. And the algorithmic question we're going to study is, in what order should we sequence these jobs? Which one should we do first? Which one should we do second? And so on, all the way up to which one should we do last. So obviously, to answer this question, we need to pin down the mathematical model a little bit more precisely. And let's start with just, what are the characteristics of jobs? What information do we have that might lead us to prefer one job over another? Well, for this problem, we're going to assume that each job comes with two known parameters. So first of all, a job J has what we're going to call a weight W sub J. That's a non-negative real number. And you should think of the weight of a job as quantifying its importance. That is, jobs with a higher weight in some sense deserve to be processed earlier than those with a lower weight. And secondly, each job J is going to come with a non-negative length L sub J. Now, depending on the application, you may or may not have a good estimate of how long jobs are going to take. But for today, to keep things simple, let's assume that we know what the length of every job is. And that's L sub J. It's part of the input to our problem. So we've now defined the input to this computational problem. We get n jobs, each specified by a weight and a length. And we know that the output is going to be a sequence of these n jobs in some order. So what we have to understand now is, what criterion do we want to optimize? What are we trying to accomplish with this sequence? To explain that, I need to tell you about completion times of jobs. So the completion time of a job is defined hopefully in exactly the way you'd think. So for the job which is scheduled first, it's just the length of the job, because that's how long it takes to process that job. For whatever job gets scheduled second, its completion time is the length of the first job, and then the length of that job itself. So in other words, it's just the total time which elapses before that job gets completed. Okay, so in general, the completion time of a job is just the sum of the lengths of the jobs scheduled to before that job plus the length of that job itself. To make sure this is clear, let's go through a quick example. So suppose there are three jobs with lengths 1, 2, and 3. I'm not going to tell you the job weights because they're irrelevant for the purposes of computing the completion time. And let's suppose we do the schedule where we just schedule job 1 first, then job 2, then job 3. So pictorially, I'm going to represent that schedule just by stacking the jobs on top of each other with the interpretation that time starts at the bottom. So time 0 is where we schedule job 1, and then time increases as we go from the bottom to the top of the diagram. And the question then is, what are the completion times of these three jobs? Okay, so the correct answer is answer C. So for the first job, it gets scheduled first, so it's very happy, and it just takes 1 unit of time to complete, so its completion time is 1. The second job, well, it has to wait for the first job to complete, so 1 unit of time elapses, and then it itself has to complete, so that's 2 more units, so that gives it a completion time of 3. For the third job, it has to wait for the first 2 to complete, so that adds 3 to the clock, and then plus it takes 3 units of time for a total of 6. So that's the definition of job completion times. In some sense, we obviously want completion times to be as small as possible. But it's not so simple. In any given schedule, the jobs that are early on are going to have small completion times, and the jobs toward the end are going to have big completion times. So inevitably, we're going to have to trading off the completion times between different jobs. What is the optimal way to do that? Well, that depends on our objective function, and in scheduling, there's many different objective functions you might want to use. Today, I'm just going to tell you about one. It's not the only natural objective function, but it's one of several most natural objective functions. It's called minimizing the weighted sum of completion times. You translate this English phrase into mathematics in the obvious way. What you want to do is you want to minimize the sum over all n jobs of their completion time, but then multiplied by their weight Wj. Okay, so it's the sum over j of Wj times Cj, where Wj is the weight and Cj is the completion time as defined on the previous slide. If you think about it for a second, you'll realize this is equivalent to minimizing the weighted average of the completion times with the weights given as in the input. So just to make sure this makes sense, let's go back to the example that we saw. In that example, we had jobs with lengths 1, 2, and 3, and we thought about the schedule where we scheduled them in that order. To evaluate this objective function, I have to tell you their weights. So let's suppose their weights are 3, 2, and 1, respectively. In this case, the weighted sum of completion times in the schedule in the previous slide, well, first we begin with the first job, which has weight 3. Its completion time, remember, was 1. Then we have the second job with weight 2. Its completion time was 3. Then we have the third job with weight 1. Its completion time was 6. So we sum up the weighted completion times, and we get a total of 15. And I'll let you verify that, in fact, of all of the 3 factorial or 6 schedules in that example, this is, in fact, the schedule that minimizes the weighted sum of completion times. And the algorithmic question we're going to study next is, how do we do this in general? Given arbitrary input, n jobs, weights, and lengths, what is the sequence that minimizes the sum over all n factorial sequences you might consider?